Let's take a look now at refrigerators and heat engines, both of which are processes that have a change in both pressure and volume of a gas while it's in a confined system. We have a diagram of our refrigerator where we have a compressor, and that squeezes the gas into a smaller volume. It goes along a skinny tube, reaches a place where it expands, goes along a fat tube, and then we have change going on where a phase change occurs. So we have two places where phase changes occur, position A and position C, and we have two places where volumes changes occur, position B and position D. Let's start at position D, and we'll move from D to A. So we have a liquid, it's at a low temperature, and it's colder than the air outside. So we have a cool liquid. The refrigerant is cooler than the air in the refrigerator. So as the refrigerant is passing along the walls of the refrigerator, it absorbs heat energy from the air inside the refrigerator, and that lowers the refrigerator's internal air temperature, and the energy transferred into the liquid increases the liquid's temperature, and the liquid refrigerant starts to boil. So at position A, we're adding heat because it's absorbing heat energy from the air of the refrigerator. There's no work being done because the volume is not changing. Because heat is being added, the internal energy of the system refrigerant is increasing. Now we're going to travel from A to B. We now have a cool gas, and it enters into the compressor. The compressor does work on the gas because it decreases its volume, pressurizing it, but it doesn't add any heat. So this is called an adiabatic process. Remember, adiabatic means there's no heat transferred into or out of the system. So the pressure increases, the internal energy, and therefore the temperature of the gas increases. So that's why we're going from the blue dots to the red dots. So in position B, I have no heat transfer, but I am doing work on the gas, so that's negative. And because I'm doing work on the gas, the internal energy of the gas increases. Okay, now so we have this nice warm gas, leaves the compressor, and it passes along the coils on the outside of the refrigerator. It is warmer than the air outside the refrigerator, and so heat is going to move from the hot gas out into the surroundings. So this refrigerant gas is giving up its energy, heat's leaving. As the heat leaves, it condenses, so I go from gas to a liquid. Heat is being given off, so Q is negative. No work is being done because the volume is not changing. Since heat is being given off and no work is being done, the internal energy of the refrigerant is decreasing. Okay, so now we have this warm liquid. It's condensed, it's still warm, not as warm as the gas, and we hit this region. What we have is a valve that increases the volume of the liquid by allowing it to flow into a larger size container. So essentially the liquid is doing work, creating the expansion. So again, we have adiabatic expansion of our fluid going on. There's no heat transfer into or out of the system, but we have work involved again, and therefore a change in internal energy. So no heat transfer, it's adiabatic. Work is being done by the liquid, in this case, so it's positive, and because work is being done by the gas, the internal energy is decreasing, causing the temperature to decrease. So that's how a refrigerator works. For refrigerators, it's a cyclic process, and we have a net work done on the gas. Now let's take a look at heat engines. Heat engines are different because what we have here is net work is done by the gas. Okay, if we start here, position A, we have heat energy being absorbed by the fluid. So we have fluid in here. Comes from the sun, and what it does is it increases the pressure. So we have heat coming in, no work is done because volume of our fluid doesn't change. And because heat is increased, the internal energy increases. So the pressure of the fluid increases because its volume doesn't change, and its internal energy increases. So it goes along to, usually we have a turbine here or something that the hot gas under pressure can push. So this would be position B. And what goes on here is now our gas is going to cause some sort of cylinder to rotate. So our gas is doing work. It's work done by the gas. We don't have any heat moving into or out of our system, so Q is 0. And because work is being done, our internal energy is decreasing. So we have an adiabatic process. So now the gas has given up its energy. It's lower in internal energy. It's also lower in temperature. And it hits our heat radiator. Here the energy is given off to the surroundings. So we get nice cool gas. Volume doesn't change. So we have heat leaving the system. That means Q is negative. Again, our volume doesn't change, so we have no work being done. And because our temperature is decreasing, our internal energy is decreasing. So our temperature decreases as well as our pressure decreasing. Another way to look at a net work equation is to look at the difference between the heat energy at the hot temperature and the heat energy at the cool temperature. Let's take a look at efficiency for a thermodynamic system. It's the amount of useful energy created in a cyclic process. It's the amount of useful energy created in a cyclic process. And we compare that then to the total amount of energy involved. So the efficiency equals the net work, which is what's coming out, divided by the hot thermal energy input. So we also learned that net work is Q hot minus Q cold. We take that over Q hot. We can also get 1 minus Q cold over Q hot. So we don't necessarily have to know the net work created to find the efficiency of the system if we know the two amounts of heat energy involved. So Q cold is energy removed by heat, and Q hot is heat energy added. If we take a look at an example of this, we're looking for the efficiency of a gasoline engine. If we look at one cycle, it receives 204.5 joules of energy from combustion and loses 153.3 joules of heat by the exhaust. So if it receives, this is going to be Q hot, and if it loses, this is going to be Q cold. Generally, Q hot is greater than Q cold, otherwise it doesn't make sense. So our efficiency is going to be 1 minus Q cold, 153.3, over Q hot, 204.5. So we get 0.25. So we have a 25% efficiency of this particular engine. And that looks at the difference between refrigerators and heat engines. They're the same idea or same process, but in the heat engine's case, the work is done by the gas. For a refrigerator, in general, the work is done on the gas, and that's the difference between the two of them.